I started looking more into this thing I'm defining for you guys as the Stratanovich product. And I'm starting to think I actually kind of invented this. Because, you know, my authorities.
Don't formally introduce that before?
Yeah, what people define is the Stratanovich integral.
I see.
And I get the notation circle S from this Chirk-John guy. But he also tries to attempt to do stochastic calculus on Lie groups. But he never figures out how to use the Maurer-Cartan 1 form. And so I turned the rule that's obviously true for the integral into this for the purpose of doing the Maurer-Cartan calculations we're doing.
Mm-hmm.
And I might be the first person to do that. So
it makes sense to me. Make a lot of sense. Yeah, please.
Yeah. Well, we'll see. Yeah, time will tell. But I was like listening to my lecture and like, you know, because I'm like, I think Chirk-John said this. I'm like, oh God, I don't know. So I look and yeah, and sure enough. Yeah. Okay. Hey, Hillary, welcome. Stochastic. Oh. Hillary, did you watch last time?
No, I haven't got around to it. I spent the weekend nursing a migraine.
Oh, I'm so sorry to hear it. No worries.
But
Just got to think. Modifying Maurer-Cartan stochastic differential. Oh, is migraines a thing for you?
yeah, if I get short on iron.
If you get what?
Short on iron.
Oh,
Right.
okay.
So I just have to take iron tablets and not have tea.
Mm-hmm. Do you like liver?
Pardon?
Do you like liver?
I don't eat it.
Yeah.
But
I hear that's good, high in iron.
I have,
Or blood sausage, maybe?
no, not for me, but I have some very good iron tablets which work.
Okay. And it doesn't upset your stomach?
No. They're
Okay.
expensive iron tablets because they don't upset your stomach. Cost $1 a pill. But they're very good.
I'll probably won't start for another 5 minutes, just so you guys know. Just got to get this stuff on the board. Oops. Wait a minute, what? Oh. You teleported.
I caught up with where the reflection was on the blackboard, so I had to move. So it was going to be somewhere.
Those rays.
Yeah.
Oops. Okay.
Where's the asterisk from?
Which asterisk?
Got an asterisk over the implications arrow. Where,
Oh, I just wanted to connect that. Thank you for reminding me. I just wanted to say that's connected to this.
Okay.
So,
That's right where I caught it.
yeah.
Okay.
That this guy is this guy. Yeah. Absolutely.
Right. Okay.
Cool. Thank you.
You're welcome. So we're back with the monster surds again.
With the what?
Well, if you put something in one of those big square root signs, one of the names for that, slightly old-fashioned, is to call it a surd.
A surd?
Yep.
The root is called a surd?
Slightly old-fashioned name for it. But...
Yes, we're back to the old surds.
Yep. So yeah, back to the monster surds.
Monster surds, yep. Yeah. The absurd surds.
I did not say that.
Yeah, there is a point to them, but you don't see it very often, so it does make people think twice. What is he doing?
And I'm glad I'm not typesetting that.
Okay, I said I was going to get started in a moment, in 5 minutes. So I will get started now since we're 20 minutes in. Okay. Wait, let me just make sure my camera guy. I think there's a camera guy. Yeah.
Tim's check. While I write the last two.
All good to go?
Oh,
Okay. And yeah, I'm just starting really late. Yeah. Okay. Okay. Yeah. So, yeah. Today we're going to learn about right invariant derivatives. I think one of the most awkward things for me during last class was I started talking about these pictures in my head, and I realized I hadn't given you guys this final tool to draw these pictures. And that tool is the right invariant derivative. Okay. So, and that's going to allow us to reach the final corner of the stochastic trinity, okay, using those right invariant derivatives. So for today, to get us started off, I'm just recalling what we did last time, which was I introduced you guys to two new tools. One of them was this Stratonovich product, and the other was this stochastic differential equation for the time-ordered exponential. And I was very lazy about where I was putting this xt inverse, because when it comes to equating things, you do it however you want. But the reality is that this is a distinct object in differential geometry. Yeah. But you can think of this over here or over here, however you please. Yeah, so I was explaining that the time-ordered exponential, which I'm expressing universally here, okay, is equivalent to this equation. And we applied it to a simple example, which was diffusive homodyne. I sort of brought out of nowhere this decomposition. Okay. How you coordinatize Lie groups is an art in and of itself. But really, there's only like 3 different ways you can do it. And most of the time, because of historical reasons, group theorists have only thought in terms of simple Lie groups. So like I would call this a Harish-Chandra decomposition, but mathematicians would argue with me because Harish-Chandra was designed for semi-simple Lie groups. And this is not a semi-simple Lie group, but I can argue for many reasons why this is the solvable analog of the Harish-Chandra decomposition. Anyway, so I sort of brought this out of nowhere. So I'm going to call this the Harish-Chandra decomposition. Or in fact, I'm going to say it a little more suggestively. I'm going to call these Harish-Chandra coordinates. Okay, so the rule was that we saw the generator of diffusive homodyne looked like this. And if you just calculate commutators, you see that you have this 3-dimensional algebra. And then with that 3-dimensional algebra, I said that means the group, the Krauss operators live in a manifold that's still 3-dimensional. And then I pulled this out of a hat and said this is a great way to coordinatize that 3-dimensional manifold. So we did some exercises and derived pretty simply what these derivatives with respect to the Harish-Chandra coordinates are. Okay? And we arrived at that. And by arriving at these equations, it was pretty straightforward what to do to get the SDEs for the Harish-Chandra coordinates. Okay? Again, and all of this was an application of these two tools that I had introduced. Okay? So were there any questions about that? I'm being a little more careful now about, there was this point about stochasticizing, and I guess a point to make here is all of this in blue. I don't know if you can tell that this is white and this is blue.
Yeah.
Yeah. But here in blue, we did forget completely for a moment that there was a stochastic trajectory in this manifold. So this really was just differential geometry, coordinatizing. But then once you had this, right, you could stochasticize the whole thing. And that just meant, now that we know, this is still just differential geometry, but stochasticized. And so because you do that, you stick in these Srutanovich products everywhere. There's a function and a differential. And then this is me now invoking the diffusive measuring process again. Okay. And that's where suddenly these differentials become equated to some process. Okay. So maybe to emphasize that one more time, there's no process in this part, right? This is all just coordinate transformations. And then here is the process. So maybe I'll emphasize that.
So the process means just
The diffusive measuring process. Yeah, exactly. Yeah. So in fact, it's this thing, right? That something is happening, there's a tracer that's squiggling around. Yeah. So, returning to the process. Okay. So, are there any questions about that part?
I have maybe trivial one. It's like, I think we give this example after we introduce the tool, but the previous two example is just completely derived from beta through. That's
well, and yeah, the fact that, so in the first two examples, so you're talking about like single Hermitian Lindblad, and yeah. In single Hermitian Lindblad, you didn't need to do something like this because all the exponentials commuted.
Yeah.
And so you could just use the fact that e to the x times e to the y is e to the x plus y. So you didn't need anything sophisticated to add up the Wiener increments. Yeah. And then in the second example, we used a commutation identity. But we could have done that like this. And you'd get something that looks just like this too, except there's a complex increment. Yeah.
And this is what you will call the most general approach to whatever.
Yeah, it is a completely general approach that can be solved when the instrumental group is finite dimensional. Okay. So there's finite dimensional.
And also with finite generator.
With
finite generator.
I guess that would be part of it, yeah. So I haven't talked about measurement chaos, which is what happens when even you have a finite number of generators, but the Lie algebra explodes into something infinite dimensional. So that hasn't happened yet in our examples, and in fact, Rob asked for me to address that. But and I will tomorrow, Thursday, yeah. So this scenario, so when the instrumental group is finite dimensional, the name I give that is principal. It's a principal instrument versus a chaotic one. So yeah, that's the main caveat. You have to establish a finite dimensional instrument, and then this will work just fine. This, again, being, I told you that this coordinate system, I pulled it out of a hat. So there's actually 3 different ways, good ways to coordinatize these manifolds. And I named them after Harish-Chandra, Cartan, and Iwasawa. And these are canonical decompositions in semi-simple Lie group theory. So how you coordinatize a finite dimensional group is another important aspect. Yeah. Yeah. Did that answer your question as far as like general approach, what it takes to do this? Yeah. Okay. Yeah, lots of moving parts. Are there any other questions or comments? I've written a few papers on much harder problems, and so a lot of the stuff I just said to you is written. Okay, oops. Okay, so today we're going to talk about another tool. So last time we were talking about these time-ordered exponentials instead as stochastic differential equations. But going all the way back, right, all of the diffusive measurements I'm talking about, they always have Krauss operators of this form. And basically, we've been zooming in lately on this part of the Krauss operator. And now, today, I want to focus on this part. Okay. So maybe you guys remember, I think we were in the space room at that time. I did another simpler exercise where I collected Krauss operators and basically was able to solve for this distribution function, but when the addition of the Wiener increments was trivial, you just add them up. Okay. So basically what I'm going to do today is the general analog of that exercise. Okay. Cool. All right. So in order to do that, we're going to need a new kind of derivative that is much more natural for these diffusive processes, these non-commutative diffusive processes. Okay. And that tool is the right invariant derivative. Okay. So I guess I need to be formal. Let x in G be an element of a Lie algebra, element of a Lie algebra, okay. And every time I say Lie algebra, I don't have to say this, but I'm just going to, finite dimensional. I actually, I honestly can't figure out how far along the theory of infinite dimensional Lie algebras has developed. There is some important stuff there, the Korteweg-de Vries equation, etc. There are significant developments there. So I think a lot of the statements I'm making are more general than I'm going to, but just to be safe, I always mean finite dimensional. So let x in G be an element of a finite dimensional Lie algebra with a universal covering group big G. And I haven't really talked about why this exists, how you construct it. I'm just basically saying when you solve time-ordered exponentials, this is where you are. Yeah. So it took decades to really figure out what this is, why it exists, how to construct it. And I'm totally finessing that part. Universal covering group G, and let x be a point and G be a point. So this kind of emphasizes, I'm thinking of G as a manifold. Okay, I could call it a group element, but I really am thinking of it as a place where Krauss operators can be. Okay, then the right invariant derivative of a function f in the direction x at the point. Okay, I should put serifs on these big x's. Direction x at a point little x is. So I put a under arrow on the Lie algebra element. Okay. So this is a differential operator. It takes a function, and that function at a point x is, okay, the limit as h goes to 0 of f of e to the hx little x minus f of x h. Okay. Okay. Can you guys see that basically the main point to appreciate is this is a point that is arbitrarily close to x. Okay. And the group rule is allowing us to differentiate, to depart from a point in a different way than a coordinate derivative parts. Okay. Okay. And this is my notation. One of the guys in quantum gravity, Rodrigo, likes this. Under arrow to the left. So maybe you understand why I put this arrow here is because it's changing x off to the left. Okay. Okay. Are there any questions about the definition? So I'll explain why it's called a right invariant derivative. Okay. So, properties. Noise. I'm going to close the door. Oh. Sorry, I'm not ready to talk about properties just yet. So translation operators. Maybe I should experiment with this. So I've started calling these kinds of operators ultra operators. Because these functions of the group elements have their own space. These don't live in Hilbert space, and they don't even live in like superoperator space. They live in their own functional space. And so because, operators, I think of operators as acting on Hilbert space, superoperators as acting on duals of von Neumann algebras. Ultra operators act on their own space, the space of functions of Krauss operators. Okay. So take it as you will. You don't need to buy the ultra word, but I've started using it, and the last paper I wrote emphasized it quite a bit because I think mentioning that there's these 3 different kinds of function spaces you can be acting on, it's helpful. I have no better word. Ultra is not super. Hyper operator usually means super operator, so ultra, yeah. Have you guys ever seen ultra used in Okay.
I think so. And the only other alternative I can think of is meta operators.
Meta, yeah.
Like something to do with Facebook.
I got ultra from, there was some interesting work in harmonic analysis in radio technology. So this term ultra harmonic emerged for a short period in dynamics research. I have no idea if this is related to that, but that's the only time I've seen the word ultra. So, yeah, okay. It's up for grabs, perhaps. Okay, so translation operators. So, of course, there's two kinds. So there's left translation and right translation. So left translation is given an element G in the group. So again, this is just for functions of the group. So then L sub G of F of X. This, by definition, is going to be F of G inverse X. And this one is going to be R sub G of F. And X is F of X G inverse. Okay? So the reason for the inverse, it goes back to high school geometry. This funny point that shifting the function to the right is the same thing as subtracting off of the argument, right? So think of F of X minus H, right? Think of how F of X minus H is to the right. Right is in the positive direction, is translated like. So if this is the x-axis, and say f was like this, at some bump x0, right, then the point is that f of x minus h has a bump at x0 plus h. Okay. So that's the positive x direction. So that's me just trying to explain why there's an inverse here. Okay. A lot of people get hung up about wanting this to be a group homomorphism, not an anti-homomorphism. But if you think hard, these are homomorphisms, these are anti-homomorphisms. But I care about the geometric fact that you're taking a bump at the identity and putting it at G. Okay. And there's a reason why they have opposite torsion. Anyway, yeah, just in case you're experiencing any of that conflict. Are there any questions, comments?
Okay. Just maybe you will mention that, like, is that part of the reason that you have to go with the right invariant derivative, not the left one later on?
Oh, so we'll need a little bit of use for both of them. But yeah, the main, why is there a symmetry breaking, if you will? And the point is the standard, right, is, oops, sorry. So this was not quite right. There's no inverse here. Okay. The standard is that time is going from right to left in these equations. So that's what's breaking left and right. Yeah. So time is always continuing on the left. The future or the present is on the left, and the past is on the right. Yep. Yep. Good. Yeah, so indeed there's no left-right symmetry. By no means is there left-right symmetry. Okay, I even use different T's for the translations. I'm just noticing hyphen little t, space big T. I didn't mean to do that. Okay, So those are the translation operators. And now there's two properties. So two properties. And I'm going to leave this for you guys to, well, I'm going to explain one of them a little bit, but this first one I'll leave for you guys to just plug in the definitions. So these things I called right invariant derivatives, sure enough, if you think about how they transform under right translation, okay, they are invariant. Okay, so this is where the name comes from. So right invariant is short for right translation invariant. Okay. Sure enough, X is right translation invariant. Okay, as the name sort of promises. Okay, 2 is a little freakier. So I guess I'll do this in a different color. If F is analytic, okay, then this translated F, and now put serifs again. Okay, so I can do this. I can take any element of the Lie algebra and start to translate away from a position X. So this is just a group element some distance away now from X. This is in fact the same thing as this Taylor series. Okay, so this is kind of a big one, that if you just think of X to the right, right invariant X as like ddx on the real line, right? Then this is just the statement that X plus, so think of F of X plus A. That's the same as e to the A ddx of F at X. Okay. So this is exactly the same kind of statement. Lately, I've started using the term group analysis to emphasize everything that you see in real and complex analysis. A lot of the stuff you see in real and complex analysis just relies on ddx being a right invariant vector field. So it's amazing how far you can go just letting go of commutativity. Yeah. Okay, are there any questions there? I'm going to call this Taylor's theorem. Non-commutative Taylor. If you want more, I do write quite a bit about this in my latest paper. So let me just write that down. For more, see archive, what is this, 2510. One 13980. Okay. Yeah. Any questions or comments?
Maybe a naive one is if would this like just wondering what happens if I act the e to the power of h x bar to the right of the x?
Would you say that again?
Like inside the function f, if e to the h bar x is acting to the right of x, will
Okay.
there be something similar?
Yeah.
It's like, great.
Absolutely. So, indeed. So I've only focused on two of the sides. So okay, I'll cover this too. So similarly,
Just curious, it's not so important if you.
yeah. Like if I put an arrow down here to the right, I would call that a left invariant derivative, and that would be me putting this over here. Okay. So let me write that down. So similarly, so we won't have a use for these, but just to satisfy your curiosity. So you can define left invariant derivatives. Where you use f of x to the x e to the hx. Okay. And with that, and then this implies another Taylor theorem, right? That f of x e to the hx. Indeed, that would be e to the hx left invariant.
Yeah.
So indeed, the operators in the way we write operators in functional analysis, they're still on the left. I still write them on the left, but the derivative changes. Yeah. Yeah. Cool. But then I'll emphasize, because it can be pretty dizzying, right, left, right, left, right. We're not going to need these guys. But we won't need these.
Arrow reverse direction.
Yeah. Yeah. Oh, absolutely.
There.
Absolutely. Yeah.
Right.
Yeah. So notice when I changed this arrow direction, I'm now talking about left invariant derivatives. So we've got two different kinds of invariant derivatives. Again, don't think too hard about it. Just focus on this one. But it is different. It's a different derivative. I wasn't planning on recognizing its existence, but yeah, Hujo could not help himself. Are there any other questions or comments? Okay. Okay, so I just introduced the right invariant derivative. So now I'm going to show you guys how to use it to get the Fokker-Planck-Kolmogorov equation for the Krauss operator density. So, okay. I'm just thinking of the plan of attack. Okay, so I need to define, so definition. The Krauss operator distribution is for a diffusive measurement for a time t is d mu sub t of x is sum over all Wiener paths with the constraint that they end up in the same place in the group. Okay, does anybody, so remember gamma of dw, you should, so maybe I can write. So if I'm like drawing the instrumental group, this manifold, and in it is the identity, and the zero time measurement is the identity Krauss operator, but then there are all these other Krauss operators. I could get x, and there's going to be many different measurement records that actually could end up there. Okay. So I'm adding up all of the different raw data outputs that would give exactly the same Krauss operator. Okay.
Is that x equals gamma blah supposed to be the lower limit of the integral, or is it just written underneath?
It is a constraint. This is a path integral, so yeah, it's not a limit, it's a constraint. It's summing over all dw such that gamma of dw is x.
Right, so it is attached to the integral rather than just being written underneath it.
Oh, it's definitely attached to the integral, yeah. And good. Are there any other questions or comments? All right, so let's crank this thing out. So again, when we were in the space room, I did a very similar kind of exercise, but then I just wrote, some variable equals integral dw. So this really is just the non-abelian generalization of what it means to add dw's. Okay? So we're adding them according to the more general time-ordered exponential rule right up there. Okay, so I don't know what to title this part. Okay, deriving did I spell that correctly? Deriving
Yeah, I think that's all right.
the Chapman-Kolmogorov equation. Just to sort of put this stuff in context. Okay, so what do? All we do is we think about incrementing the time. Okay. So maybe I'll write it like this. Okay, so what is the Krauss operator distribution at t plus dt? Okay. So this is where I need to just follow my notes because I can't think live. Okay, we'll go through this nice and slow. So this is integral x equals gamma of dw going from 0 to t plus dt. Okay, so far all I'm doing is changing the increment, right, or the time. Okay, nothing profound there. But then, what is that? So remember the Wiener increments, all the Wiener increments are independent. So I can just take out the integral over dw at time t. And I could have vectors over everything. Right, this doesn't have to be. Did I put vectors before? I did. Okay, so I can take out of this measure the last Wiener increment. Okay. And does everybody see how I did that? I just pluck out the last increment. And also, down here, I'm going to explicitly write out. So remember, these are time-ordered exponentials. So I can, again, take out the contribution from the last moment in time. And that's just e to the, what I've been calling delta t. Okay. So e to the delta, okay? So delta t does have an increment in it. So in fact, maybe let me write this instead as delta of dw t. That's probably going to be a little clearer. Okay? Does anybody want me to write down what delta of dw is? I can point at it. Yeah, I can help you find it. I think I wrote it up here. Yeah, here's delta. Okay. Technically, you know, delta didn't have to be, so delta is that for diffusive measurements, but, you know, if you just forgot about quantum mechanics and where our delta came from, you know, this could be any stochastic process on a Lie group. So, yeah. Delta is what it is. Okay. All right, so then what is that? I'm not going to write the next line. I'm just going to write this part. Of course, this is the same constraint as me writing this guy on the left. Okay? That's the same set of x's. The set of x's such that this is true is the same as the set of x's such that that's true. Okay. So then, let me keep this down for a second. In that case, so maybe I'll do this in a couple colors. Ooh. So there was this observation, and then I'll just do this in a new line. So that means star is equal to so can you guys recognize if I write it like this, this is t, this is t. So this is in fact the same thing as d mu at big T, except that the position argument's a little different. Okay, great. So all of that is just d mu, so big T of e to the minus delta of dwt x full stop. Okay, so that's okay. So this is the Chapman-Kolmogorov equation. Okay, maybe I'll just rewrite the first line. Therefore, d mu of t plus dt at x is just an integral over the last increment, the same distribution evaluated the time before. Okay. So I guess I could draw a picture for that. I keep relocating my chalks. Let's see. I'm like a squirrel. Where did I put my chalk? There we go. So the picture that goes with this is, if I've got some path, then there's the sort of last dW, right? And the point is there's all the places you could go before you get to x, right? So there's the distribution of this point earlier, and then you're just summing over all of the places that get you there. Right? So we're basically summing over all of these. And then if we knew the distribution at each one of those previous points, we'd be able to calculate the distribution at the new point in time. Okay. I hope that helped. So that's great, but that doesn't allow us to calculate anything analytically. So now we need a little bit more. So now I need to define a new object. So okay, so this is where you got to pay attention to the words. So I previously defined the Krauss operator distribution. That's what this d mu t of x is. But now I'm going to define the Krauss operator density. Okay. And I call this thing the KOD because it's such a central object in diffusive measurement. Is okay. So right, dt of x is d mu t of x divided by the left invariant Haar measure. So again, pedagogically, this wasn't the, I forgot to introduce this. So this thing, so two things here, right? This thing is the left invariant integral measure, sometimes called the Haar measure. Okay. So it has the property that if I take some other point, this has the same measure as the original point if I multiply on the left. Okay. So there the picture is that at any, it's like this cube, if you will, at gx has the same volume as this cube at x. Okay. You've got this measure, this sort of cube size equipped at every point in space. Okay.
This is something always associated to the Lie group.
Yeah, so a group, there's a name for groups that have Haar measures. They're called locally compact topological groups. Okay, so it's a mouthful, locally compact topological group. In fact, so the Haar measure was invented in 1933. And I think one of the most interesting things about the Haar measure is it actually surprised von Neumann that it exists. It's a kind of window into one of the limitations of von Neumann's perspective. So if you really think about, like, von Neumann was such an influence by 33 on the foundations of quantum mechanics. And somehow the way he thought about analysis and how these things work, he was surprised that the Haar measure existed and could be constructed explicitly quite easily. I sometimes wonder, I commented some weeks ago about Scott Aaronson barking at me for believing in uniform distributions. I think of that as the same thing. Von Neumann was surprised, because so Haar measure is what I call a uniform distribution. And if you're Scott Aaronson, you would bark at me for, that's like a ridiculous definition to him of a uniform distribution. Well, to me, I think this is a perfectly good definition of a uniform distribution. So it shows there's a psychological thing there. Yeah. If you're obsessed with measure theory on the real line and the like Stilt-Gies-Lebesgue way of thinking, and that stuff was invented, in 1909, the Riesz representation theorem, etc. A lot happened in the next 20 years. This idea of topological groups, etc., and how that gave birth to stochastic calculus. Yeah, so who knows how many people even understand that? Okay, so a lot going on with the Haar measure. Did I answer your question, Yuja?
Yeah.
Okay. Yeah. And so that was one tool, and then the second tool was this quotient. So this quotient is called the Radon-Nikodym derivative. And if I were you, I wouldn't think too hard about this. Just think about what this allows us to do. Okay. But these things have names. Okay. In that case, the denominator is called a dominant measure, okay? Because this one is a multiple of this one. So you could say things like, dx on the real line is dominant to, God, how do you say that? It majorizes the Gaussian. Like a Gaussian is a product of a function and dx. But dx is not an integrable function times a Gaussian. Right? So anyway, basically all distribution functions can do is concentrate stuff. Yeah. So this is sort of the ultimate unconcentrated measure, and groups have them. Yeah. Okay. Are there any questions here? Radon had a special role in the development of quantum tomography. Yeah. So I always like seeing his name. Okay, so now, how much time do I have? 20 minutes, great. Okay, so now we're going to derive the Fokker-Planck-Kolmogorov equation for the Krauss operator density. So this is a totally excessive name, right? But I'm like covering all my bases. The Fokker-Planck-Kolmogorov forward equation. For the KOD. Okay, so again, the term is pretty excessive. You could just say the Fokker-Planck equation. You could just say the Kolmogorov equation. You could just say the forward equation, Kolmogorov forward equation. Okay, but I think this is like the largest name you could give this.
What did Planck have to do with it?
Oh, yeah. Planck actually spent the rest of his career trying to argue that you could just use classical probability theory to explain quantum mechanics. So Fokker was a student of his. He basically didn't like the unreality of the wave function. So he spent a lot of time developing the theory of generalized heat equations. Yeah. Yeah. So that's why his name's on it. He spent a ton of time hoping that the Schrodinger equation was equivalent to a Fokker-Planck equation, things like that. Yeah. I don't know exactly what he was thinking. I mean, that's sort of the suggestion. I know that Planck tried to see if you could replace quantum mechanics with classical probability, right? So the rest of it is me just making assumptions about why he thought that, etc. Okay? Did I answer your question?
Yeah.
Okay.
Context is good.
Yeah, absolutely. And then Kolmogorov would have been doing this work at the same time. But I don't think they were communicating. And Kolmogorov was not concerned about quantum mechanics at all, I think, yeah. So, in any case, regardless of what Planck wanted, there was work there to be done. Classical probability. Because, right, distributions are also pretty unreal, right? Distribution functions are like the belief of the agent, or, they have just as much of a, what is this thing that allows people to make money? Like there's a reality to it, but it's, what is the term, latent? Liminal is even a term I've seen mathematicians use. Liminal, the liminal nature of distribution functions, latent nature, right? It has consequences, but it itself doesn't exist. You can't point to a distribution function sitting on a table, right? It's this like highly contextual thing. Anyway.
But you can define them as limits of a supertask, though.
Right. I mean, there's all these ways to argue why they're real. So latent exactly refers to that you can reveal them by sampling over and over again.
Yep.
Yeah. But then it only exists latently, like it can be arbitrarily manifested. Yeah. Cool.
I might use the word implicitly, but
Implicit?
it's defined as a limit. But actually, liminal is quite a good pun, really, for saying it only exists as a limit.
Liminal is a term that Demir used, who is a member of Bourbaki, mathematician that I have a lot of respect for, in the context of C-star algebras. And I can see, part of the paper I just wrote was this connection between C-star algebras and distribution sequential measurements. So I made that connection between C-star and sampling. So yeah, I'd be curious to know who else liked this term liminal. Demir is considered out of date. He wrote this textbook back in the 60s.
I mean, liminal just refers to being on a shore. It's on a boundary rather than being a limit.
Right, yeah.
So it's kind of a pun rather than a correct usage.
Yeah.
I mean, it's gotten so obscure that, it might well be a candidate for being reassigned, like words sometimes are.
Let's talk a little more about this after.
Yeah.
That word liminal is very interesting to me.
Instead of getting into word games.
Yeah, absolutely. Okay, gotta derive the Fokker-Planck equation like I promised. Okay, so the main thing to notice, so first thing you should ask yourself is, well, Chris, why did you divide by the left invariant R measure? Why not the right? Right? And the point is that, so I'll just write, why? Because we have this guy, right? So naturally, because the stochastic process is piling up operators from right to left, right, that ended up with a Kolmogorov equation with left translations in it, a Chapman-Kolmogorov equation. So that means that if this, Gesundheit.
Gesundheit.
Yeah, Gesundheit. Okay, so if I write this out, right, then this is just equal to this. Okay, so that's me just plugging in the definition of the radon. So this really is what you mean. You say there exists a function such that this is a multiple of this. That's what this really means. It's not actually a method of calculating. It's just a formal statement of something that presumably exists. And so then the point is, if we do everything relative to the left invariant measure, well, this part has exactly the property that you want it to. So then what does that mean? Well, if you look at the Chapman-Kolmogorov equation, right, then this part has a dlx, and so does this part. So you can just drop the dlx. And so that allows us, the existence of this left invariant measure is precisely what allows us to turn the Chapman-Kolmogorov equation into a Fokker-Planck equation. Okay? You need something like that to exist. Otherwise, you don't have a Fokker-Planck equation. Okay. So hopefully I just convinced you that we can drop the dlx's. Okay, so therefore, maybe I'll write in orange. So, therefore, star. Star. Therefore, integral d mu. So remember, these are just Wiener measures when I write d mu of dw. Hopefully my use of d mu's isn't too confusing. Okay, so is everybody happy with that? I just wrote the Chapman-Kolmogorov equation, then dropped the dlx's. Okay, hopefully that's the same thing. Yeah. Maybe not being very consistent about my big T's, but otherwise. Okay. All right. Okay, so now I'm just going to, this is a dummy variable, right? So I'm just going to not put a t here. Okay, so I'm just integrating over the dw's, but there isn't actually a time dependence in here. It's just the last Wiener increment. So now I'm giving it a name that doesn't care about its time. Okay, now here's where we can actually do something. So check it out. This thing, if dt is an analytic function, we can use that non-commutative Taylor's theorem I just told you about. Okay, so this is in fact the same thing as taking dt and translating it by these invariant derivatives. Okay, so that's why we needed to transition from distributions to densities, because densities are actually functions, right? So that left invariant measure allowed us to step into a different category, okay, where we can do this. Okay. So then what is this? So now we need to remember what delta is. So going back to diffusive measurement, right? So then this thing, right, is just e to the minus sum on I, li root kappa dw I sub t plus, derivative plus q, derivative kappa dt. Okay, so I just plugged in what delta is, and advanced these operators. Turned these operators into invariant vector fields. I was going to draw you guys a picture for example 3, so I'll do that after I finish this derivation. Because, again, I told you guys I have this picture in my head, and I haven't drawn you what those pictures are. But basically, these invariant derivatives, you can think of them as vector fields. You can see them. Okay.
How should I think about d mu dw? It's like...
Yeah. So this guy, of course, is, so good question, because we're going to need that step in a moment. So don't forget, this guy is just the product of all the dw's. dw1,
Yeah.
d mu, dw, n. Okay. Does that answer your question, or? Yeah.
But for each individual one of them, what kind of measure I should think about it? Or it's like
Each of them is a Wiener measure. So every d mu of dw is, and this was the thing I was saying some time ago about nobody writes this. You remember this guy? Yeah.
Yeah.
Oh, no worries. Again, nobody writes this because this part is just so
Weird.
weird. Einstein wrote this distribution down in 1905, but he calls this big delta. Okay. But he has this picture in his head. He doesn't know the difference between left and right invariant derivatives, etc. And there's actually a huge, like, the Maxwell-Boltzmann distribution is on the other side of the Chapman-Kolmogorov equation. So there's all of these subtleties about left versus right, even in the commutative case. Anyway, I digress. So every d mu of dw is just a zero mean Gaussian distribution with variance dt. Yes, and we're about to use that. Okay, so this board doesn't move. I'm gonna move this up so I can use the bottom of this board. Okay, so let's see here. Can you guys see? So this is equal to e to the q kappa dt, and then product I equals 1 to n d mu of dwi e to the minus li root kappa dwi. I'm putting t's on here when I said I wouldn't. Yeah, sorry. That's just a dummy variable in an integral. Okay, does everybody believe that? And just wrote the product of things and the thing. Okay, and now comes the important part. Would either of you stick around if I went 20 minutes over?
I'm free.
You would? Okay. Because this part's gonna finish up in 5 minutes, but then I want to do the example. So actually, that does mean I want to keep this part. So, Okay, so we're just wrapping up over there. So continuing where I left off. So we've got one right invariant derivative in the direction q. And then these Gaussian integrals, right, we can just do them. Yeah. And when we do them, that's where the second order differential operators come from. Okay, so I'm going to write a second order differential operator as just this, right invariant, right invariant. Yeah, and remember all of this is being applied to the Krauss operator density. Okay. Are there any questions about that? Just did the Gaussian integral. Remember, these integrals are Gaussian because they're universal for independent sequential measurements. Okay. And this is, well, now I can just use the fact that dt is small. So this is 1 plus kappa dt, some operator. Ultra operator, if you want to call it. Okay. Everybody buy that part? I've just done 1 plus a little bit, 1 plus a little bit, and then plus all the little bits. Oops, maybe I'm missing a parenthesis. Okay, so therefore, now we have ourselves the Fokker-Planck-Kolmogorov equation, right? Because this whole thing, remember, is d at t plus dt, right? So that means that this part is the time derivative, the partial time derivative. Okay, so therefore, ddt of dt of x is kappa, this thing. So this is the Fokker-Planck the Fokker-Planck-Kolmogorov forward equation for the Krauss operator density of a diffusive measurement. Okay, so mission accomplished. That was the general result that we wanted to show today. This is the third corner of the stochastic trinity in its application to diffusive measurement.
Just a very naive question. It's like, solving this, you still need to know the initial.
Yeah, the initial condition is always the identity measurement.
I see. It's always that. Okay,
Yeah.
got it.
It could be whatever instrument you started off with, but I usually think there's no measurement yet. So you have the identity distribution function. All your Krauss operators are identity at t equals 0. Yep. And indeed, that's, yeah, so maybe I should write that with initial condition. d0 of x equals what I would call the delta function, but remember this is the delta function for the group. Okay, so group's delta function. So lots of technical detail there, but loosely speaking, you know, this thing is 0 everywhere except x equals the identity. Alrighty. Are there any other questions? now I'm just going to do the optical homodyne example. So I've got to make sure I don't erase any optical homodyne information. Okay, so example. Back to example 3. Okay, so now I'm going to say something kind of subtle. So try to pay attention. Okay, so this is me just writing what I erased. Okay, so last time we calculated these guys, right? Calculated these guys last time. So now that we have the right invariant derivative, I can actually pluck these guys off of the x. Okay. So in the same thing as these equations, okay, I could instead write partial r is minus L dagger L's right invariant derivative. Because remember, this differentiating x is just this times x, right? So, okay, so let's see. So using that, say y of x is yx. So here, what I'm thinking of is, there's a couple different ways you could think of this. But yeah, if x is a representation of the group, then by definition, this is what you get on the left-hand side. You differentiate it. So you can think of it as like x is some family of eigenfunctions. Okay, so I'm going to use that. And then the point is, because x is the position, if these are equal on the position, they're equal on any function of the position. So then I can just drop the x entirely. And that took me years to get used to, but it's true. Okay, so that's that one. And then similarly, partial s is e to the minus r L squared. And partial q is e to the half r. Sorry, there's no minuses there. There's no minus. Whew. Okay, so these are the same equations as those equations. So now I'm going to draw you guys a picture. Okay. So I could just as well, I'm going to do some Blackboard magic first. Okay. Hillary, I'm sorry. So I'm just going to move this on this side. Okay. So the same thing here. Okay, because if I do it that way, then you can now think of this as a transformation. I've literally written these invariant vector fields in a coordinate basis. Okay? And you can see from this, the picture that the the POVM stops evolving. Okay. In particular, so if I zoom in on, say, QR coordinates, okay. Where did I put red? If I want to write the vector field minus L dagger L, well, that's just partial R. Okay, so that just is this vector field. It looks the same no matter where you are. Okay, it points up. So what that means is every moment in time, the Krauss operator steps up. Okay, so that's one part of the evolution. And then the other part is, that's critical. So if I write this guy, that guy is partial Q, but exponentially decayed. So that means that depending on, if you're at the same, R value has the same length, but then as you go up, it starts to decay. Okay? And you never go down here, you always go up.
Being in the coordinate system, R is always greater than 0.
Yeah, because remember, you ended up with R equals kappa T.
I see.
So the measurement just always takes you up.
And you also mentioned once that R can be think of as the squeezing level.
Would you say that again?
I think you mentioned maybe last time, like R can be thought about the squeezing level of the...
Are you saying squeezing?
Yes. Squeezing.
Yeah, so that's this third dimension I'm not drawing.
I see, okay.
So that one keeps advancing as well. Yeah, more and more squeeze. Yep. Good. So here, do you see what I'm drawing now? That if you're at the same R value, these arrows are the same. Okay. So like if I just plotted partial Q, right, that would be the same arrow everywhere pointing to the right. But this is partial Q, but then shrunk down by R. Okay. So these are just vector fields on a manifold. Okay. And the whole process is that every moment in time you increment by one of these, and then you randomly go left and right depending on this. And so the steps become smaller and smaller as you go up. The right invariant process translates to this kind of freezing out effect. I have a feeling, I don't know a lot of quantum field theory, but I've heard the term non-abelian confinement. And I have a feeling this is the same feature, that the POVM turning off because of the non-abelianity, the non-commutativity, must be the same thing. But we're not talking about potentials of gauge fields. So it's a little bit of a stretch for me to think they must be the same, but hey. Okay. So that's that. So then I can write you guys what the Fokker-Planck equation looks like for this case. And then we'll be done. Are there any questions or comments? No? Okay, so finally, example 3 continued. So we can just plug these guys into the FPKE, the Fokker-Planck-Kolmogorov equation. Okay, and what do you get? Where's my... Thank you. So remember Q, Q always has two pieces in it, right? In this case, because there's just one Lindblad operator, there's the positive Hermitian piece, and then there's this L squared piece. So, so the Fokker-Planck-Kolmogorov equation is time derivatives of the distribution function equals. So Q is just half L dagger L right invariant derivative plus half L squared right invariant derivative plus, am I getting this right? I think I'm getting it right. Okay, and this is where, like, your head can start to spin. But so far, so good. We've got these first order derivatives in these quadratic directions. And then we've got these second order differential operators in these linear directions. Okay, so totally different kind of square, right? In this case, like this kind of square is just some linearly independent direction in the instrumental group. But this first order derivative is what's saying that the evolution of the corresponding direction is ballistic. It's not diffusing in these directions, it's diffusing in this direction. Second order means diffusing. First order means flying. Okay. So, well, we have these vectors. So this is just over there. Minus half partial r, and then minus half e to the minus r partial s, and then plus half e to the minus r partial q partial q. Okay, so hopefully that looks more like a second order partial differential equation to you guys, because it's got coordinate derivatives in it. Yep. All right, and well, sure enough, it has a solution. That's pretty easy to write down. Solution is so extra fact, we didn't calculate the left invariant vector fields, okay? But if you actually calculate the left invariant Haar measure in RSQ coordinates, guess what? It's just dr ds dq. Okay. Kind of what you might guess immediately. The right invariant measure is not this. Okay, so the solution is so dt of, remember we've got our coordinate systems. This is the definition of x equals, oops. Right, this was just the definition of the RSQ coordinates. Sure enough, you get a delta in the r direction, moving delta in the s direction, but then diffusion in the q direction. And the diffusion in the q direction is no longer standard diffusion, right? Instead, you get a time-dependent variance, which looks like very similar to this part, actually. 2 kappa 1 minus e to the minus half kappa t. Okay. So one of the things it's saying here is this Gaussian doesn't just diffuse arbitrarily wide. It actually stops diffusing. Yeah, have you guys heard of Ornstein-Uhlenbeck processes? Is a all back in this Fokker-Planck time, some physicists were trying to think about diffusive processes that make a Gaussian stable. So a lot of thought's gone into these things, and sure enough, Ornstein-Uhlenbeck processes happen naturally in these non-commutative settings, which is interesting. I don't think they knew that. I'd have loved to talk to Ornstein or Uhlenbeck. Okay, I think that's it for today.